All right, Module 28. I thought there were more that were from previous modules, but I guess not. So there's these 4 from previous modules. The first 3 are from really early on. And then the last one there is that classifying conics was just from 2 modules ago in Module 26. So revisiting that one. But we're going to start with complex fraction involving univariate monomials. So if you notice, you have already done this using multivariate monomials. So univariate is actually a little bit easier. I think it was probably in module 4 that you did the one with multivariate. But anyways, we'll start with this. So you're just simplifying a complex fraction, which means it's a fraction within a fraction. So we have something like 21x cubed over x minus 5 over 3x squared over x plus 5. Okay, so you're dividing 2 fractions, so you have to do it like you're multiplying by the reciprocal. Okay, so we would rewrite this as 21x cubed over x minus 5 times x plus 5 over 3x squared. Okay, and then you simplify what you can simplify. So in this case here, we've got an x cubed over an x squared, which will leave us with an x. We have a 21 over a 3, which will leave us with a 7. And we can't do anything with the x plus 5 and the x minus 5. So we're going to just leave that as x plus 5 and then an x minus 5. And that's it. Okay. The one thing you might remember me showing you guys is that if you think that you will want to cancel things out, circle them. So like this 21 over 3, if I circle them, if I don't go through addition and subtraction signs, then I can cancel them. Okay, so like right here, I sliced through a multiplication sign, and right here, I sliced through like what would be a multiplication sign. So that's okay. But if I thought maybe I wanted to simplify these x's and I circle them, I go through an addition sign and a subtraction sign, and that's not okay. All right, so that's kind of a little rule of thumb there that you can try. Okay. All right, then we got the next one here, which is, I want to make sure that I'm not repeating the next one. Okay, the next one that is sequentially in the module is the complex fraction quadratic factoring, which you've already had. And then we get some complex fraction made of sums involving rational expressions, problem types 1 and 4. So you have not had those yet. Okay, so our next one is complex fraction made of sums involving rational expressions. And this is problem type 1. Okay, so for this one, again, we'll have fractions within fractions, but we're going to have a sum. Okay, so we're going to have the numerator will be 5 over 2v minus 7, and the denominator will be 5 over 2v minus 3. Okay, so we just want to simplify this. Generally, we don't want to have fractions inside of fractions, so we try to clear our fractions. Okay, and this actually, it looks really confusing, but really, all you need to do is multiply by 2v over 2v. Okay, what that's going to accomplish then is it cancels out the denominators in each of those individual little fractions. So when we have 5 over 2v times 2v, we just get 5. When we have 7 times 2v, we get 14v. Okay, and then the denominator will work similarly. So I'll end up with 5 minus 14v, because there's a subtraction sign there. Okay, and then 5 minus 6v, because when I distribute that 2v in the bottom. Okay, and that's it. That's all you got to do. Again, like I said before, you can't reduce those 5s. that require you going through a subtraction sign. And same, and this is the one that's a little tricky. 5 minus 14v over 5 minus 6v. If you do circle the v's, you don't go through a subtraction sign. But those are two that you can't cancel those out. Okay. You'd have to be able to factor them out of the whole expression, which you can't do there. So we have to leave those. Okay. And if you think about it too, like you could plug in a number, if I plug in 1 for v, so if v equals 1, then I would have 5 minus 14, which is negative 9, over 5 minus 6, which is negative 1, which is 9. Okay. Or if I plugged in v equals 2, I would get something different. Okay. But if I tried to cancel out the v's and simplify it down, it's just a constant. And so it doesn't change if I change my v. Okay. So just don't be careful of that. Don't cancel out those v's. Okay. It does look like these problems are all going to be pretty similar to that one. So hopefully there's nothing too tricky there. Let me just double check here. Yeah, they're all going to be real similar. Okay. Next one, we have the same topic, but it's problem type 4. So we have our, again, complex fraction made of sums involving rational expressions, but it's problem type 4. Okay, so an example of this type, we have 8 over y minus 1 plus 8 over 8 over y plus 1 minus 8. Okay, so it's a little similar, but now the denominators are two different expressions. Before we had the 2v and the 2v. Okay, but now we have y minus 1 and y plus 1. All right, so all you need to do is you multiply everything by y plus 1 times y minus 1. Okay, so again, I'll do the numerator is two separate pieces. So if I do 8 over y minus 1, oops, not y minus y minus 1, and I multiply it by y plus 1 times y minus 1, these y minus 1s cancel out, and I have 8 times y plus 1. Okay, so that's what's going to happen with that first piece there with the fraction. And then if I do the 8 times y plus 1 times y minus 1, that's all I get. And then I can just expand it. So like up here, I could have 8y plus 8. All right. And then here, I'm going to have 8. Remember, your difference of squares factoring. Y plus 1 times y minus 1 is y squared minus 1. So I'll have 8y squared minus 8. Okay. So what I end up with then in my numerator is 8y plus 8 plus 8y squared minus 8. Okay, when I do the same thing in the denominator, so that 8 over y plus 1 times y plus 1 times y minus 1, the y plus 1s cancel out. So then, here, I'll just even do it over here. Okay, the y plus 1s cancel, and I have 8 times y minus 1. So I have 8y minus 8. Okay, and then I have an 8 again, which is what I already did right here. Okay, so then I'll have 8y minus 8 minus 8y squared minus 8. Okay, and then I'll simplify those. So I've got a bunch of 8s going on. So I'm just going to take out the parentheses. And then when I take out the parentheses on the bottom, I just need to make sure I distribute that negative. So it'll be minus 8y squared plus 8. Okay, and I can see that on both the numerator and the denominator, I have a plus 8 and a minus 8. So I'll have 8y plus 8y squared over 8y minus 8y squared. Okay, so I've simplified it down quite a bit. I'm not done yet. There's more I can do here. I can factor out an 8y in the numerator, which leaves me with 1 plus y. And in the denominator, I'm left with 1 minus y. So those 8y's cancel, and my final answer is 1 plus y over 1 minus y. Okay. So just be real careful with the negative there. I have a feeling these are all going to be similar types of problems. Yeah, it looks like it to me. Okay, so always look for that little factoring at the end where you can simplify them more, because it looks like that will happen quite often. Okay. In fact, you know what? I'll see if I can find another good one to do. Okay. I'm going to do another one for you, just because these do get kind of tedious here. Let's get one more. So we have 1 minus x plus 2 over 4x plus 20 over 2 plus 2 over x plus 5. Okay. This one you want to be careful too, because what you really have here is 1 minus x plus 2 over 4 times x plus 5, and then 2 plus 2 over x plus 5. So when you clear your fractions, we don't need to multiply, the tendency would be to multiply by 4x plus 20 and x plus 5. You only need to multiply by 4x plus 20 on the top and the bottom, because that will clear your fractions. Okay. So what I'm going to end up with when I distribute it to here, I'll have 4x plus 20. And then I'll do minus, when I distribute it to here, the 4x plus 20 is going to cancel. Because remember that 4x plus 5 is just 4x plus 20. Okay, so then I have x plus 2. And then in the denominator, I'm going to have 2 times 4x plus 20. And then again, if I multiply it by this, what I end up with is 2 over x plus 5 times 4 times x plus 5. So those x plus 5s cancel out, and I just have 8. Okay, so then when I take out my parentheses, I have 4x plus 20 minus x minus 2 over, I'm going to distribute this. So I'll have 8x plus 40 plus 8. Okay. So now 4x minus x will give me 3x plus 18 over 8x plus 48. Okay, and then just like before, it looks to me like I can factor out a 3 from the numerator and leave myself with an x plus 6. And I can factor out an 8 from the denominator and leave myself with x plus 6. Those x plus 6's cancel, so I'll have 3/8. Okay. Let's see. I think that should be enough for you, but let me know. As always, don't be shy about asking if you need help. Okay. Then we have, I'm just matching these up here. So I just did we need quotient involving a monomial. The one that I don't need to do is complex fractions, variable in the denominator. Okay. Rational expressions. Sorry, I'm trying to match up what I need to give you and what you've already had. Okay, so I see it now. I just don't need to do variable in the denominator. Okay. All right, I'm back. So our next one is rationalizing a denominator quotient involving a monomial. Okay, and I'm just going to get myself set up for the next one. It's going to be rationalizing a denominator using conjugates. Integer numerator. Okay. All right, so for the first one, we have square root 2y over square root 3. Okay, and we want to, again, rationalize the denominator, which means that we would multiply by square root of 3 over square root of 3. Okay, so we'll have square root of 2y times square root of 3 over square root of 3 times square root of 3. All right, so, and remember, we can combine these. So the square root of 2y times the square root of 3 would be the square root of 2y times 3. Okay, now square root of 3 times square root of 3, that's just 3. Okay, you're basically doing the square root of 3 squared, and those are inverses, so they undo each other. Okay, the other thing you can think about is doing it like the square root of 3 times square root of 3, which would be square root of 9, which is 3. Okay, but that's going to be it then. So your final answer is square root of 6y over 3. Okay, it's going to be that simple for those. I can try to grab another one here for you. If we have, yeah, it's real similar. Square root of 2z over square root of 5. Multiply by square root of 5 over square root of 5, and we end up with square root of 10z over 5. Okay? A little easier than the one before it there. Next one. Okay, this would be like if I have something that looks like negative 3 over 3 square root of 5 minus 4. Okay, now remember conjugates, a plus b, a minus b. Okay, so you just multiply by the conjugate. So we're going to multiply this by square root of 3 square root of 5 plus 4 over 3 square root of 5 plus 4. Okay, so now if you multiply conjugates, you have a plus b times a minus b, which is going to be just a squared minus b squared. Okay, if you do an area model for that, a plus b, a minus b, we get a squared minus ab plus ab minus b squared. So those always cancel each other out. Okay, so you can use that shortcut there. So we'll have negative 3 root 5 plus 4 over, we can do 3 square root of 5 times 3 square root of 5 minus 4 times 4. Okay, so what we end up with then is negative 9 square root of 5 minus 12 over 3 times 3 is 9, square root of 5 times square root of 5 is 5, so 9 times 5, which would be 45, minus 16. So we have negative 9 root 5 minus 12 over 45 minus 16 is 29. Okay, so that's your final answer there. I can do another one for you there. This one we have 3 over 5 minus 2 square root of 2. Rationalize the denominator, so we're going to multiply by 5 plus 2 square root of 2. Okay, so we distribute that 3, so we'll have 15 plus 6 root 2. And then we can do 5 times 5, which is 25, minus 2 root 2 times 2 root 2, which is 4 times 2, 2 times 2 is 2. Root 2 times root 2 is 2. So it's 8. So I have 15 plus 6 root 2. And 25 minus 8 is going to be 17. And that's your answer. Okay. Let's see here. The next one, when I was checking it before, you've already had using a variable in the denominator. That's from a previous one. Complex fraction made of sums involving rational expressions, type 5. That was from a previous one. And classifying your conics was also just from a couple modules ago. Okay, so the next new one is we're getting to arithmetic and geometric sequences. So I remember teaching these in Algebra 2. Okay, we are going to go over here. I'll do some notes here quick. Arithmetic and geometric sequences. Okay, so for your arithmetic sequences, we have a constant difference between terms. So an example of an arithmetic sequence would be like 2, 7, 12, 17. We're adding 5 each time. Okay, geometric would have a constant ratio. So it would be maybe like, well, let's start with 2 and we could multiply by 5 every time. Okay, so times 5, times 5, times 5. Okay. Seeing. Okay, it looks like they generally just give the sequence to you and have you find the terms. Okay, you might remember that you're explicit for a geometric, just in case it comes up. Each term is that constant difference times n plus the initial term. You know what? I'm not going to do that right now because I don't want to give you a different notation than what Alex uses. Okay, so let's just start with their topics there. I don't want to lead you down the wrong track and then have to change how you're writing things. So let's just get started right away. Okay, the first topic is finding the first terms. If you guys have your interactive notebooks from Algebra 2, you have all this good stuff in there. Using an explicit rule. Okay. So in this one, we have a sub n equals 43 minus 5 times n minus 1. Okay, that's your explicit rule. So like if I wanted to find the 100th term, I wanted to find a sub 100, I can just plug 100 in for n. So it'd be 43 minus 5 times 99. Okay, I can tell from this that we are subtracting 5. Okay, because that's that number right there. So wherever we start, we're going to be subtracting 5 to get to the next terms. Okay, and they also tell us that we start with an n of 1. Okay, so your first term would be 43 minus 5 times 1 minus 1. So 43 minus 5 times 0. So that's just going to be 43. Okay. Your next term, second term, would be 43 minus 5 times 2 minus 1. So 43 minus 5 times 1. So that's just going to be 38. Okay. You are supposed to find the first 4 terms. We could keep doing this All right, or we can see, well, I just have to subtract 5 every time. So 43, 38, minus 5, minus 5. And that's your answer. Okay. Next, we're going to do the same thing with geometric. So finding the first terms of a geometric sequence using an explicit rule. Okay, so these are going to look a little bit more like exponential functions. So we'd have something like 7 times 2 to the n minus 1, where n equals 1, 2, 3, and so on. So our first term is 7 times 2 to the 1 minus 1, which is 7 times 2 to the 0. And if you remember, anything to the 0 power is just 1, so we get 7. Okay, your second term. So now again, I can tell that the multiplier is 2. So I know the second term is going to be 14. Okay, I'll show the math there. It'd be to the 2 minus 1 power, so 7 times 2 to the first, which would be 7 times 2, which is 14. Okay, again, I know I'm just going to multiply by 2 every time. So it's 7, 14, 28, 56. That's it. Okay, I could go ahead and keep going. For my third term, it would be to the 3 minus 1 power, 7 times 2 squared, 7 times 4, which is 28. Okay. All right. Next, we have finding the first terms of a sequence using an explicit rule with multiple occurrences of n. So these are neither arithmetic nor geometric, but they just give, it's just a formula, guys. That's all they're doing. They're giving you a formula and you plug in some numbers, okay? So a sub n is negative 1 to the n plus 1 times 3n squared for n equals 1, 2, 3, and so on, okay? So your first term here is negative 1 to the 1 plus 1, 3 to the 1 squared. So negative 1 squared times 3 times 1. So that'd be 1 times 3 times 1, which is just 3. Okay. And then I can plug in my 2. My second term would be negative 1 to the 2 plus 1 times 3 times 2 squared. So negative 1, so the shortcut for this negative 1 is if it's an even power, it's going to be a positive 1. If it's an odd power, it's going to be a negative 1. So negative 1 to the third is going to be negative 1 times 3 times 4. So I'll have negative 12. Okay. And unlike the other two, there's no easy pattern to pick up on these. All right, we just got to find them all. Okay, so our next one, we'll have negative 1 to the 3 plus 1 times 3 times 3 squared. So we will have positive 1 times 3 times 9, which is 27. And then finally, your fourth term, negative 1 to the 4 plus 1, so that's going to give us a negative 1 times 3 times 4 squared. So times 3 times 16, so we have negative 48. So our first four terms, 3, negative 12, 27, negative 48. There we go. Okay. Next one is finding the first terms of a sequence using a recursive rule. Okay, so we've been doing explicit where you just have to plug in the term that you want and we'll get it. If you guys remember, the recursive rule, you have to use the term before it. So finding the first terms of a sequence using a recursive rule. Okay, so with your recursive rule, remember you have to have one term. Okay, so we have the first term. We have to have a rule for getting the other terms. So any term is equal to 4 times the term before it. That's what a sub n minus 1 means, plus 10. And that's going to be true for n greater than or equal to 2. And the reason we say that is because we already know what the first term is. So then we're going to use this rule for any additional terms. Okay? So we're supposed to list the first 4 terms. Well, the first term is easy. The first term is negative 5. Okay. The second term would be when n equals 2. So a sub 2 will equal 4 times a sub 2 minus 1. Right? I'm just replacing the n with a 2 plus 10, which means it will be 4 times a sub 1 plus 10. And I know what a sub 1 is. It's negative 5. Okay, so I'm going to have negative 20 plus 10, which will be negative 10. Okay, my third term will be 4 times the second term plus 10. So it'll be 4 times negative 10 plus 10. So negative 40 plus 10 is negative 30. And then my fourth term will be 4 times the third term plus 10. So 4 times negative 30 plus 10, which is negative 120 plus 10, so negative 110. Okay, so my first 4 terms would be negative 5, negative 10, negative 30, negative 110. Okay. Next, we have factorial expressions. All right, these are kind of fun. You've seen these, maybe you've seen them a little bit, maybe. Factorial expressions. So first of all, we need to know what a factorial is, okay? N factorial would be n times n minus 1 times n minus 2, all the way down to 3, 2, 1. Okay, so like 5 factorial would be 5 times 4 times 3 times 2 times 1, which ends up being actually 120. Okay, so in this example, we have 5 factorial over 7 factorial over 6 factorial times 4 factorial. Okay, now here's the trick here. You're not going to have a calculator for these, but you simplify them. Okay, so 5 factorial will be 5 times 4 times 3 times 2 times 1. 7 factorial will be 7 times 6 times 5 times 4 times 3 times 2 times 1. 6 factorial and 4 factorial. Okay, and what happens is huge chunks of these cancel out. This can cancel out with this, just like that. This can cancel out with this, just like that. Okay, so we're just left with 5 times 7, which is 35. Okay, and you definitely don't need to write them out the whole time like that. Okay, another example, 2 factorial over 7 factorial and 4 factorial over 8 factorial. Take the biggest ones. Okay, so like 7 factorial over 8 factorial, that's just going to be an 8 left in the denominator. Okay, And then 2 factorial over 4 factorial, that's just going to be a 4 times 3 in the denominator, because then the 2 and the 1 cancel out. So we need a 1. We need a placeholder in the numerator there. But that would be 1 over 4 times 3 times 8, so 12 times 8, which is 80 plus 16, so 96. Okay. So those are nice. Make sure you are not using a calculator for those. If you're using a calculator, you're doing more work than you need, because it's quicker. Here, let's do another one. It's quicker to just do it without a calculator. You could do it without a calculator faster than I could do it with a calculator. This one's kind of a repeat of up there, but okay, my 2 biggest ones will leave a 7 in the denominator. My 2 smallest ones will leave a 5. It's 1 over 35. Faster than you can put it in a calculator. Okay. All right. Then our last one from this module. We're getting so close to being done here. Finding the next terms of an arithmetic sequence with integers. Okay, so this one, they don't actually give you the rule. Okay, they just give you, here's my sequence, the first 3 terms. Okay, find the next 2. So they tell you it's arithmetic. So we mean we're going to constant difference. Sorry. Okay, so we got to think about, what do we add or subtract to get to the next term? Okay, so -5 to 2 to 9. Well, to get from -5 to 2, I add 7. To get from 2 to 9, I add 7. So there's my rule. Okay, the next one would be 16. And then after that, I'd have 23. Okay, so the next 2 terms are 16 and 23. And that's it. That's all you need to do. Okay, and that is it for this module.